This lecture is about the line sizing calculation. We will see an example problem of how to determine the pipe size for a given operation. Let us say you have to calculate the line size for a flow rate of 300 meter cube per hour to transport water or some process fluid, and you have the pipe roughness of zero point 0.4, and the length of the pipeline is 100 meters. If you consider a schedule 40 pipe, that value is given to look for the thickness, and the viscosity of the flowing fluid is 1 centipoise. You need to assume a pump discharge with a velocity of 1 to 3 meter per second. So if you require to calculate the pipe size for this following operation, first you need to fix the velocity. That is, you need to assume a velocity as given in the problem within the range of 1 to 3 meter per second. So if you look at the various velocity ranges for the fluids, if you have a superheated steam, the recommended velocity range is 40 to 75 meter per second. In the case of saturated steam, which is ready to condense, that is in the range of 20 to 40 degree for 40 meter per second. Then wet steam is in the range of 20 to 30 meter per second. If you are going to consider water, in the case of pump suction lines, the velocity range is 0.5 to 1.5 meter per second. The pump delivery lines will consider a velocity range of 1 to 3 meter per second. The boiler feed discharge will be having a recommended velocity range of 3 meter per second to 3.6 meter per second. Then if you're going to transport heavy oils, the recommended velocity range is in the range of 1 to 2 meter per second. Then light oils are also in the range of 1 to 2 meter per second, because those are all viscous fluids. So here for our problem, we are going to consider the water because the viscosity is given as 1 centipoise, and the pump delivery line should be operating with a recommended velocity range of 1 to 3 meter per second. So based on this recommendation, we go for the assumed value of velocity as 2.5 meter per second. Then using the continuity equation, we determine the diameter of this pipeline. The continuity equation is Q is equal to A into V. So the area can be written as pi d square by 4 because of circular cross section. So D is equal to 4 times of Q, that is the flow rate, divided by 3.14 into the velocity to the power of half. So substituting the values of the flow rate, which is given as 300, then uh, converting for hours to seconds, you use the 3600. Velocity is 2.5 meter per second, that is the assumed value of velocity. We calculate the diameter of the pipeline as 0.206 meter. So that is 206 millimeters. So the internal cross section area corresponding to this diameter will be given by the pi r square. It is 3.14 into 206 by 2 squared. So the internal cross section area is determined as 0.3241 square meters. Next, we need to find out whether the flow is turbulent or laminar. We calculate the Reynolds number and we determine that it is greater than 2000. So the flow is turbulent for this particular operation. So since the flow is turbulent, we apply the Moody's chart and find out the values of the friction factor. The roughness and the diameter are utilized to calculate the roughness by diameter ratio. Depending upon these two values of the Reynolds number and the roughness to diameter ratio, we determine the friction factor as 0.024. Now this friction factor is used to calculate the pressure drop. So that is given by the Darcy's Weisbach equation, which is uh, delta P is equal to FLV square density by 2 GD. So substitute the values of friction factor 0.024 into the density of water, then the velocity divided by the viscosity, then acceleration, not viscosity, that's the acceleration due to gravity, and the diameter. So this will be giving you the conversions of the units in kg per square centimeter. So we calculate the delta P, and this delta P is in terms of H, and if our allowable pressure drop is less than this 0.3983 kg per square centimeter, then we can consider the diameter of the pipeline that we determined. So we also have to look at some standard diameters which is close to our calculated value. If our value is close to some standard diameters, then we have to choose that standard dimension and we estimate the pressure drop based on that diameter of the line. So if we have standard diameters available, you calculate the pressure drop for that standard diameter, and then we check whether it is less than the allowable pressure drop. So if it is less than the allowable pressure drop, then we can go for the standard size of the pipeline. Considering the schedule number, we need to look at the schedule number to determine the thickness of this line so that it satisfies the pressure and the temperature rating. So this is a small calculation which indicates how to perform the line sizing for an incompressible flow when you have water that is getting discharged in the velocity range of 1 to 3 meter per second.